Okay, let's take a look at the generalization problem. So we've got our graph, and we've talked about the fact that let's just get that we have to have this endpoint, and we have to know what that is in order for us to continue with the graph. So we know that that point is 14 and 1.5. If you don't know that, then you're going to have to substitute in, say, the 14 into your existing equation that you got for your graph, and find out what the y value is, or whatever it is that you're going to have to do. So we know that we're going to get a graph that comes down like this, and we're going to probably model that as a quadratic. And so it doesn't really matter. This thing is basically going to hit, right, and have a minimum value down around here. It could be any one of these points. You know, it could be 16 and 0, it could be 17 and 0, it could be 18 and 0, 19 and 0, but we have a minimum point. But instead of actually naming it, which is what we had to do to create the equation for the model, we just label that point as n0. So n could be sort of basically any one of these values, 15, 16, 17, 18, 19. Now, we've got the basic frame of the equation, which is this, x minus, now, this is going to be the shift, so this is like our n, so we're going to say minus n squared. Now normally we have the plus b, which is a move up and down, but we don't have a move up and down for this particular situation. So basically this is the frame of our equation right here. This is the general frame. But we don't know what k is, so in order to make a generalization so that we could basically put any point into our general equation to get the model of this graph, we need to represent k as a generalization. So we need to find out what k is in terms of x and n and so on. So what we do is we're going to rearrange this formula in terms of k. So we're going to make k the subject. So we're going to basically divide by x minus n squared, x minus n squared. So we're going to end up getting k to be the subject, and it's going to be in terms of y over x minus n squared. Okay, so we can put values in for y and x. I mean, we could have probably done this, should have probably done this earlier. But if we go back, we know that there's a point that we're going to use of 14 and 1.5. So all we're going to do is stick that point in here, so we don't have all these unknowns. We only have k in terms of basically n. And so in this particular case, y is 1.5 and x is 14. Should have brackets around it, by the way. Equals k. So what we've done is we've created a general expression for what the stretch of the quadratic is going to be, starting from 14 and 1.5 as a point, as the beginning point. And we don't have a value for n. N could be anything greater than 14, basically. If we plug this in for any point, 16 and 0, 17 and 0, 18 and 0, we will be able to figure out what the stretch for this graph is to get it to go from 14 and 1.5 down to the ground. Now we're not quite done yet, because what we want to do is we want to have the entire equation in general terms. So if the equation was y is equal to k times x minus n squared And we know now that k can be expressed this way, okay, using the point and n. So we're going to plug that in for k. We're just going to substitute in. So we're going to get y is equal to 1.5 over 14 minus n squared times x minus n squared. Right? And so what we've got is we've got a general expression that will enable us to basically find, this is a generalization for what we did up here, so that we could use that procedure for finding any an equation for any point along this line down here.